applications, IV characteristics, that is important. So construction mainly, this is same, construction is same for any PN junction. Okay. First, suppose here we will take mostly compound semiconductor. Okay, compound semiconductor. So in these semiconductors, here also we can make gallium arsenide wafers. Okay, we'll make wafers. This is also possible. Okay, anything we can make it as a wafers, but different. Suppose if you take wafer, first they without, let's mute what is muting. So okay, suppose here we will take n plus region. N plus means doped n type semiconductor, heavily doped. On this we will deposit a p type layer. Okay, p plus or p type p layer. Okay, add moderate dope. Moderate means not heavily. Okay, this is heavily doped. Okay, high impurities are added. P moderate means moderately doping was done. Okay, so this is PN junction. You can take NP or PN, whatever our convenient way we can take. But mostly P layer is upper layer will take. Okay, emitter layer will take as a emitter layer. Okay, so this is just PN junction is done. So in the bottom to collect charge carriers, to collect current. Okay, this will make one metal layer. This is metal or conducting layer. Metal layer or conducting layer, whatever you can say. Here metal aluminum, gold, platinum, copper. Okay, like this any metal can be used depend on our requirement, and we'll also optimize each layer. Optimize each layer to get best performance of
Sir, your
LEDs.
voice
Okay,
is breaking, sir.
so in the top also, top side also we'll two electrodes here. Just a second. So top side also we'll make so is it okay now? Can you hear me clearly?
It is breaking, sir.
No, sir.
Still it is coming breaking. Just a second, I'm making. Plus now is it okay? Can you hear me clearly now?
Now also breaking, sir.
Hello. Still. Now please check it. Is it okay?
Now okay, sir.
Yes, sir. Somewhat okay.
Oh, okay. Actually, so okay. So here we will take again here metal contacts. This also some metal contacts. Same thing you can take aluminum, silver, or gold, platinum, copper, whatever you can take here. Okay. So here we'll connect one top layer. This P layer is connecting to forward bias, right? Always LED work under forward bias. Okay. This positive terminal is connecting to P side and negative terminal is connecting to N side, plus and minus. Okay. So once you connect here, we are applying now the device is under forward bias condition. Under forward bias condition. When you connect forward bias condition, here in p-type holes will come towards the interface, and in n-type semiconductor electrons come towards the interface. At the interface, this electron hole will recombine. Electron hole recombine emit a photons. Okay, it will emit photons. So this is a loss of energy or excess energy. Okay, this will emit in the form of photons. Okay, this is photons. So the photon color will depend on what type of band gap material we have taken. Okay, mainly band gap or material. This will photon color will depends on band gap or material. That we have we have already solved this one. 1240 by this Eg. Eg, if you take Eg in electron volts, the lambda in comes in nanometer. Okay, depends on band gap, our wavelength will be changed. So each material having different band gap. Okay, so emitted photon color will depends on band gap or material. That is the thing. Okay, this is the construction. Okay, how other ways you can make this p type and n layer also. You can make solution process solution, you can have solution and you can make it, or you can make a chemical vapor deposition. This is also one method, chemical. This preparation you can search in Google or something, YouTube also. Physical vapor deposition. So in this also what we will do, there is a chamber inside. Okay, here one positive electrode and negative electrode is there. Okay, here you will connect a some high frequency power. Okay, RF power. Okay, this is like a 10 to 20 megahertz frequency we will give, or electric field, nothing but electric field will give. So in this, in between electrodes, plasma will be created. Okay, plasma will be created when we'll send here some gas material. Okay, gases will send. First we'll send gases in the chamber. We'll give the RF power. We ignite these gases or we ionize these gases and plasma will be created. This plasma will be deposited. Here we'll keep a substrate, or you can keep anywhere substrate. Then it will deposit. One layer will deposit. After that, another layer, whatever requirement gases we will send. Like that, we'll make different layers. Okay, so that we'll get the PN junction and electrodes also you can make by, you can backside you want a silver electrode, there is a pen, just you make it like a, you make, you write, just write, that will coat as a layer. Okay, that is also paste, just like a paste is there, just you paste on the back side, front side, then that will become a metal layers. Okay, this is the construction of LED. Okay, now see, after construction what we will do, we will take a dome type. Okay, dome type uh, uh, dome type shape or structure. In that we will keep a LED. We'll keep LED and we'll connect this plus and minus. Okay, here there is a insulation layers. One terminal is plus, one terminal is minus, cathode anode. Okay, so in that the photons will emit. Okay, these photons will emit when you give biasing voltage. The photon will emit and these photons will come out of the surface and we can see which color, blue or black, blue or red, green, whatever color you want to see depending on this material, we can see the color. Okay, this is the collector. So here LED material refractive index is LED. Suppose LED refractive index is always about 3 to 3.5. Okay, so here air medium refractive index is air medium. Suppose this is always 1. Air medium is always 1. So what is happening? Sometime when light hit this surface, this will reflect back. This will reflect back. When this will reflect means when angle of this incident is greater than critical angle, this will total internal reflection takes place. Total reflection, or you can say total reflection. So the light will not enter into other medium. This will reflect into same medium. So to overcome this problem, to overcome this reflection losses, we'll coat one layer here. Okay, we'll coat one layer on the dome. Okay, on the dome surface. Okay, on the surface of this layer, that is epoxy resin. Okay, epoxy resin will coat on this material. This refractive index is in between refractive index of LED and refractive index of air medium. Okay, it is less than 3 to 3.5 and greater than 1. Okay, so that there is no total reflection. Whatever light emitted from the LED, it will come out of the surface of the dome. Okay, out of the surface of the dome, then we can clearly see the light and we can reduce the losses. Okay, photon losses we can reduce, or light losses we can reduce. Okay, that is why we always choose the surfaces as a circular tape, a circular type or dome type. Okay, this way we will take. That's why we never take it's a cylinder, it a Rectangular or square type will not take. Even you also observed in many times this bulbs at our home. It's a circular type or dome type we'll see. That's why because to reduce the photon losses or light losses. That's why we will always will shape will fabricate devices in this shape. Okay, LEDs or lamps or bulbs. Okay, that is the reason. So here epoxy resin is to reduce the total reflection losses. Okay, total reflection light, suppose light is sometime light reflect on the surface of the dome. So to reduce this one, we'll coat a material that refractive index is in between LED material refractive index and air medium refractive index. That is maybe it's less than 3 to 3.5 and greater than 1. Okay, that way we will choose the epoxy resin material. Okay, this is the way we will reduce the losses. Okay, now construction and this thing is over. Now we will see IV characteristics. Okay, this is also one very important. So whenever you want to check the device, IV is the main device main characteristics to check the device properties. Okay, whether our device is working properly or not. So for that, like generally we have done already PN junction diode. This is PN junction diode. This is voltage on x-axis and current is on y-axis. Okay, are you is it clearly audible?
Yes, sir.
Okay, thank you. So voltage we are taking on the x-axis. Okay, and we are measuring the current on the y-axis. So we will increase small voltage, so there is no current. After that it is slowly starts the current. Okay, it is slowly start the current. This is the forward bias characteristics. Forward bias characteristics, because we never operate LED in reverse bias, only we will measure in forward bias. Okay, up to, so this is knee voltage. What we say, I have written VK, that is knee voltage. Up to knee voltage there is no current or very slight current. This is about 10 power minus 12 amps. That is very less current here. Minus 12 or minus 15, that is less current will be absorbed up to before 10 power minus 13 amps up to knee voltage. After that this current will increase. Why? Because there is no current, means once you junction is forming. Okay, once you junction is forming here interface, and this is the depletion region. Here whole electrons are there. This is n side and this is p side. Okay, here holes are there. So we are giving some forward bias voltage. So once you give forward bias, once the depletion region is forming, no more electrons and no more holes are not cross this barrier. Even if you increase some voltage here, these electrons get some energy and then only they will cross the barrier. Even starting voltage, these electrons or holes doesn't get that much energy, so they will not cross this barrier or depletion width. So when they will not cross depletion width, there is no current. Okay, that's why up to knee voltage there is no current. Okay, because electrons holes doesn't have that much energy to cross the depletion region. Even if you increase this voltage, forward bias voltage, this holes electron getting sufficient energy and diffuse into towards the interface, towards the junction. That time the current flow will be flow in a circuit. Okay, then we will absorb some current in a device. That is what is, there is a sharp increase in current after knee voltage. After knee voltage, even small voltage will absorb huge current in a device. Okay, this is IV characteristic of LED. Okay, if you draw the circuit diagram, okay, first what we will do here, we will take a LED material, LED, and this is plus terminal and this is minus terminal. So LED symbol is just this way. So here two arrows, why we drawn, light is emitting, that's why we have drawn two arrows. And here we are connecting forward bias plus and minus. Okay, here one more thing, here we are connecting a resistor. This is series resistor. So this is resistor. So this is the simplest. Here you can connect a ammeter to measure how much current is flowing in a circuit. You can measure using this ammeter. Okay. So here why we are connecting series resistance means sometime you will give high biasing voltage. That means huge current will flow in a device. That time there is a chance of damage of our device or LED. So in that, if you connect one resistor here, the main function of resistor is it will stop the current, right? Isn't it? It will stop the current. Once it is stopping, then only limited current flow to the limited voltage flow to the limited current flow to the device. Okay, then our device will be safe if you connect series resistance. Okay, that is why we are always connected a one small resistor for a LED circuit. Okay, this is the in practical also you will do, but once you come to lab you will do this measurement, but I don't know when you will come. So this is the thing why we are connecting resistor here. So if you write IV characteristics, do you remember PN junction IV characteristics? Do you remember? I don't know. So I, this is dark characteristics, exponential Q into V minus IRS by KT, IRS by KT. This is this is saturation current of diode, and due to diode. Okay, second one is IRS. Okay, this is an exponential Q V minus IRS by 2 kT. Okay, here 2, here 1 is there, nothing but 1 is there. If nothing is there, 1 is there. So at lower voltage it is n is equal to 1, at higher voltage n is equal to 2. So this is the ideality factor. Okay, what is ideality factor? What do you know about ideality factor in a junction, in a device? Anybody knows what is the ideality factor? Ideal factor in a device, if you say. Did you remember we have discussed when PN junction diode is, that time we have discussed this ideality factor. N is ideality factor. So if you don't know, no need to worry. Just you have to think positively. So in the question only you have answer. Ideality means what? Ideality means what? Ideal means what? Are you listening?
Yes, sir.
What is mean by ideal? If you don't know English, tell me in Telugu. I don't know. I don't have any problem. Hmm? ID
Primary.
primary. Ideal means it's a perfect, just like a perfect. Ideal. So ideal factor always indicate how our device is perfectly working, how our device is perfectly performance is perfect. Our device, how the device performance is actually following ideally, means it will indicates. Suppose in our device we have fabricated N layer and P layer, N and P layer. In that maybe at the interface there is a defects, or maybe N type layer there is a defects, or P type layer there is a defects, or metal layers there is a defects, or maybe resistance losses are there. Okay, because of these losses, our device will not behave as a perfect diode, perfect PN junction diode. So because of these defects, it will, the diode curve will partially deviate from ideal curve. That is indicate ideality factor. Ideality factor is just like a how ideally our device is performing. How ideally our device is, how ideally our LED is performing. That will indicate. That is the ideality factor. Okay. So low voltage, the first term will be dominate. Okay, first term is that is diode current. This ID and IRS is reverse saturation current. Reverse saturation current or saturation current. Okay, saturation current you can say. Okay, so this is just like a leakage current. In forward bias, you know, current due to what? Diffusion or diff in forward bias. In forward bias condition, how we will get the current? Diffusion mechanism or drifter? Drift of charge carriers or diffusion of charge carriers? In forward bias, please tell me. Or if you say in reverse bias, how we will get the current? By drift or diffusion? Hmm? If you are not able to answer, means you are not at all listening class. That is the main thing. If you listen
In
classes,
forward
you will
bias
clearly.
diffusion, reverse bias drift.
Yeah, that's good, very good. So why are you not telling? So this is diffusion process. Will get the current. That is good answer. Okay. So if you listen, you will able to answer. If you don't listen, you will not able to answer. Okay. This is drift process. Here we will use the internal electric field to get the current. Here only charge gradient. Okay. Charge gradient, because of charge gradient we will get the diffusion. Here charges are less. Only minority carriers will flow in reverse bias. That is by internal electric field. So here majority carrier will flow. Okay, majority carrier, because of the carrier concentration, higher density of charge carriers, we will get the diffusion current, here drift current. So here if you see our LED is working under forward bias condition, there is a chance of minority carrier concentration also flow from one side to other side. Minority charge carriers, this will also, minority electrons and holes also cross the junction. Because of this flow of minority carriers, there is a slight current will be generated. Addition to diffusion current. In addition to diffusion current, that is working as a in forward bias. Okay, in forward bias also some minority carriers will cross the barrier. Because of this minority carrier, we will get some less, very less current. That is we are calling leakage current. But we want only forward current. But because of this minority carrier flow, we are getting some reverse current. That is what reverse saturation current or leakage current. This always should be less. Then only our device to perfect. So that is the thing. In lower voltage, the first term will be dominate. First term will be dominate. In that case, N is 1. N is 1 means this is perfectly following our ideal diode equation. So if you increase temperature, or if you increase temperature or voltage, the resistance effect also involved. At a higher voltage, more current will flow. In that case, the resistor stops some of the current. Okay. So because of this effect of resistance, we have one more term, that is IRS term, exponentially QV into V minus RS by 2 kT. So this is at N is equal to written, right? This region due to higher voltage or higher voltage or higher temperature. Okay. This lower term is lower voltage or lower temperature. This N is equal to one region, this region. Okay. So depending on this curve, we can predict how our device is performing, what parameters are influencing our device performance. Okay, this is, that is why we always measure the IV characteristics, varying voltage. We will measure the current. From there, we will analyze this curve, and we can estimate the defects. Where is our device having problem, and we will rectify that problem while fabricating device, so that we will make a good device and will get good output. Okay, if it is a problem in a device, when you switch on the bulb, maybe it will simply blow off or will get less power. That is why there is a difficulties in, if we have a defects in fabrication, will not get the best lamps or best LED will not get. Some defect, because of this defect, it may blow off easily, or it will not give good power, or it will not sustain for a long time. Okay, this kind of problems will come. That's why Once we measure IV, we will optimize each and every step in fabrication. Once optimization is done, we will prepare a best device and we will check quality check. After that, we will release in market. Okay, that is process involved in a research side, and you will get the best product and you will see it. Okay, so these are the working of construction and working of LED and IV characteristics and diagram. So here we'll see applications. Already we have discussed many times application. These are applications. So what are the applications you know? Please tell me. What applications you know? What are the applications you know? You know this application, but somebody, if they ask exam, they will not write applications. You know, what are the applications you have in LED? Please answer me. Are you listening?
Yes, sir.
Please answer me. Applications you are seeing daily life in daily life. Where you are using this LEDs? Just tell me. Applications means uses only.
TVs, monitors,
Decorations are
Applications means
light
don't conf.
applications.
Yeah, this much you know. Applications means uses. Just it is a just different words. That's it. So TVs and mobiles,
Mobile phone
mobile phones, laptops,
traffic signals.
and traffic signals,
Right.
and household bulbs are lamps, whatever you can say. Okay, lamps, and 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 decoration items. Okay, decoration our home. Some, if it is any party, something decoration lamps, something like that, or decoration items, something like that. Okay, electronic circuits. Okay, electronic circuits also we will use this LEDs. Okay, and many applications we have. You can write many applications. And also, and this one more thing, this will use into 7 segment mode. Already we have discussed 7 segment and 5 by 7 matrix method. Okay, this how these methods are. 7 segments means here we have 0 to 9 numbers. That means you can write, if you want to write one, you can arrange LEDs in a systematic manner. Suppose if you want to write 0, you can arrange in a like this way. Okay, this way you will get. But in 5 by 7 matrix, here you can write 0 to 9, A to Z. Okay, here alpha numerical you can write. Okay, suppose you want to write A, you can write A like this. Okay, if you want to B, you can arrange LEDs in a systematic, and you can get it a get it whatever design you want, whatever number you want, whatever word you want, you can write. Okay, you can write on the display boards. Okay, these two methods are there. One is 5 7 segment and 5 by 7 matrix method. Okay, these are two things, and these are applications. And so here benefits, what are the, why we are using this much means, why benefits are features. Benefits are features, you can say. So these are, lifetime is very high. What is that? Lifetime. Lifetime, high lifetime, and small in size. Small in size, and because of the small size, wherever you want to install, you can install it. Okay, and what else?
Consumes less power.
Yeah. Cost
Yeah,
effective.
less power and very less cost. Less power. Sorry, less power consume very less power, and cost also very less. Cost also less, and easily you can operating voltage also very reasonable. That is, operating voltage is like 1.2 to 3.5 electron volts. You can operate volt, just volts. Okay, less voltage, and else it will give good power, right? Stability also good. Stability and power also good, right? It will give good power. Okay, it will generate good power. Okay, these are the few benefits. That's why we are using in very regular applications. Okay, so these are the topic of LED. Okay, So any doubts here up to in this LED topic? So suppose if you have the question, first you have to write LED definition. LED means it is a simple PN junction diode. Okay, it will convert optical electrical energy to optical energy, electrical energy to optical energy. This conversion we are calling under forward bias condition. Okay, under forward bias condition. This is definition. And this one you can say electroluminescence. What is that? Electroluminescence. So why we are saying this ones means, okay, electroluminescence means here see they are using electrical energy and producing optical energy. Electroluminescence means they are taking electrical energy producing light or photons. That is what electroluminescence. So you got it right. So photoluminescence means they will take photon energy and emits electrical energy. That is photoluminescence. But here LED is electroluminescence, same as taking electrical energy and producing optical energy. That is the electroluminescence means. Okay, so this is the LED and diagrams you have to draw. Each diagram is very important. Without diagram, whatever you write, that is not useful. And IV characteristics applications, this you have to write if they ask questions. Okay, this is long answer question, so prepare this way. And if you have any doubts you can ask me please. So this is LED working, construction and theory and applications. Benefits are advantages. So disadvantages is, oh, I forgot this one. Disadvantages, only two disadvantages are there. Okay, if you increase temperature, okay, if you increase temperature, output power will reduce. And also at higher voltage, so series resistance will influence the device performance. These two are disadvantages. So if you generally we will use the device at room temperature, but if you use at a higher temperature, the output power will reduce. And also if you operate higher voltage, series resistance will influence the device performance or device output power. Okay, these are two disadvantages. Okay, so but this always LED operate, okay, that is operate under 1.2 to 3.5 volts. Within this range the LED will operate under forward bias voltage. This is forward bias voltage. Okay, so this is the LED. Okay, so if you have doubts please ask. Now time is up. If you have doubts also you can message me or you can call me, it's not a problem. Or tomorrow also you can ask. Tomorrow we will see photo detectors. Okay, you all already many detectors you have seen, like a bomb detectors or some other detectors. Okay,